Good morning, everybody. All right, today we're going to start chapter 3. Chapter 3 deals with quadratic functions and equations. And we're also going to look at inequalities. We looked at it last in chapter 1 and a little bit in chapter 2, but we're going to look at inequalities and solving equations of inequalities. Today, I hope to cover these three topics, the first three sections of the chapter. Complex numbers, quadratic equations, functions and zeros, and we're going to analyze graphs of quadratic equations. To begin with, what are complex numbers? Complex numbers, remember, there are in the scheme of the whole number system, there are real numbers, like the counting numbers, decimals, fractions with decimals with repeating or terminating decimals. And then there's something called imaginary numbers. Imaginary numbers, this is the real definition, imaginary numbers are not real numbers. That is our definition. So in order for us to look at all the possible numbers, that answers we can get, we have to look at the real numbers and we look at the imaginary numbers. That is what a complex number is. It's made up of both imaginaries and complex numbers. Let's look at what is an imaginary number. As we said, it's not a real number. For example, it started off with this. The square root of 4. What this is asking, this radical, there's actually an invisible 2 there. That's called the root. That's why it's called a square root. If it was a 3 in there, since that's a 3, it's called a cube root. This is called a square root. So there's an invisible 2 there, which tells us what we need is 2 of the same numbers that multiply together to equal that. This one, so what makes up 4 is 2 times 2. This one says what number times itself 3 times the same number equals 8. 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. So because we have a square, 2 numbers that are the same, we can take them out of the radical. And that's how come it equals 2. Same thing here. Because we needed 3 and we have 3, this answer is 2. All right, so the root tells us the number of times a number must be repeated to take it out of the radical. The radicals are these symbols. Those are radicals. And actually, it's called the n could be any number, 2, 3, 4, 5, whatever. All right, so that's what I said here. If we have a square root, if it's even, let's say if it's a square root or a fourth root, or sixth root, eighth root, if the root is even. So 2 times 2 is 4. 16 is made up of 8 times 2. 8 is made of 2 times 4. 4 is 2 times 2. So 16 is made up of 2 times 2 times 2 times 2. Since there are 4 of them, I can take it out. So even roots can only have positive numbers inside them. Odd numbered roots like the cube root or the fifth root, if this root is odd, so 8 is made up of 2 times 2 times 2. It happens 3 times, so it comes out. 32 is 2 times 16, 2 times 8, 2 times 4, 2 times 2. So 32 is 2 times 2 times 2 times 2 times 2. It equals 5 times. Since it equals 5 times, and that's how many we need, it comes out. But with an odd root, I can take negative numbers because negative 8 is made up of negative 2 times negative 2 times negative 2. Since it happened 3 times, the answer is negative 2. Odd roots can be both positive and negative. Because we can't take the square root of negative 4. Because no two numbers, exactly the same numbers, or 2 times 2, this does not equal negative 4. That does not equal. Neither does this. 2 times 2 does not equal negative 4. So, whenever that occurs, whenever you have an even root and the number inside the radical is negative, you have an imaginary number. Or it could be eighth root of negative 28, whatever. You cannot have that negative inside there. To solve these types of problems, we remove the negative from inside the radical. But when you do that, you must place an I outside the radical. Tell us that the number is imaginary. Now, what does all that mean? So if we have the square root of -4, you can't do that because it's an even root. So we remove that negative and put an I outside. Now this I tells us that this answer had a negative inside the even root square root or even root radical. Now we can go ahead and solve this. The square root of 4 is 2 with an I. Here you have an imaginary number. Imaginary numbers came about by engineers and scientists because sometimes when they're doing the work, they ran into this problem. And because of that, they had to keep on going, so they figured out this process of making imaginary numbers. So let's put all this together. Complex numbers are made up of real numbers plus imaginary numbers. And this is the way they look. Real numbers are represented by the letter A, and imaginary have an I after them. So actually, we've been using imaginary complex numbers all along. For example, yes, a complex number could look like this, or it's got a real number and imaginary. Or it could look like this. Or this. Because in this one, the real number is 0, and the complex number, imaginary number is 6i. Same with this one. The real number is 0, and the imaginary number is -7i. Actually, these are imaginary numbers as well, because the imaginary number is 0, the coefficient is 0. So any number can be written as a complex number. The algebra of complex numbers. Remember, by algebra, we mean we can add, subtract, multiply, and divide them. And the rule here is combine like terms. We have to remember that. So let's look at addition and subtraction of complex numbers. A plus bi plus c plus di, or a plus bi minus c plus di. Two plus 3i plus 7 plus 5i. Use the same numbers over here. 2 plus 3i minus 7 plus 5i. Here are examples. As usual, is if we have parentheses, I like to keep those separated because if you have a negative or if you have a coefficient, it changes the whole equation. So do we need the parenthesis here in the first one? No. How about the second one? There's a coefficient of just 1, so we can just drop the parenthesis. Once you get rid of the parentheses, that's the general rule, whenever you get rid of parentheses, always combine like terms. So real number plus real number, so 2 plus 7 is 9. Positive 3 plus 5 is positive 8i. So there's your answer. And the other one, do we need the first one? No, because there's nothing in front of it. But this one has a negative sign in front of it. So what that does, we have to distribute that negative to everything inside there. So negative times positive is negative 7. Negative times positive is negative 5i. The negative in front just changes all the signs of the terms. We got rid of the parentheses, so combine like terms. 2 minus 7. 7 is bigger, so it's negative. 7 minus 2 is 5. That's the real numbers. Now the imaginary ones. Positive 3, negative 5. 5 is bigger than 3, so it's negative. 5 minus 3 is 2, and there's your answer. We cannot combine those two. We can also have coefficients of imaginary numbers. All it is multiply, distribute through there. So 3 times 2 is 6. Positive times positive is positive. 3 times 7 is 21i. So we can have coefficients and just distribute it to there. All right, so in this one, we have a negative. We have to distribute first by their coefficients. We can't combine them because we have to get rid of the parentheses. We can't do anything inside the parentheses, so we have to get rid of them. Negative times positive is negative. 3 times 2 is 6. Negative times positive is negative. 3 times 5 is 15i. Same with the second one. Negative times negative is positive. 4 times 5 is 20. Negative times negative is positive. 4 times 3 is 12i. We got rid of the parentheses, so it's combined like terms. Negative 6, positive 20. Opposite signs, take the sign of the larger. The answer is positive. 20 minus 6 is 14. Now, the imaginary numbers. Negative 15, positive 12. 15 is bigger, it's negative. 15 minus 12 is 3i, and there's your answer. So that's adding and subtracting complex numbers. Just nothing to it. Now, the multiplication division is a different story, because to multiply, whenever you multiply i's, you get I squared. Remember, when we had square root of negative 4, we got I radical 4, which became 2i. So remember, the negative inside the radical, the negative 1 inside the radical, is the same thing as I. So that's what happens. So it's a negative inside the radical, so it's negative 1. If we square both sides, the square root and the square cancel, so we have negative 1 equals I squared. So whenever you see an I squared, you can replace it with a negative 1. So I times I equals negative 1. So I squared equals negative 1. This is very important because we're not limited to what exponents can be, and we'll go over that in a second. So 2 plus 7i times 3 plus 4i. This is the multiplication. Of complex numbers. So we have two binomials, or two terms in each one. They're binomials. So the first term, both of these terms have to multiply both of those. So the first term times the first term, 2 times 3 is 6. Then positive times positive is positive. 2 times 4 is 8i. That's it for that one. Now we do the other one. Positive times positive is positive. 7 times 3 is 21i. Positive times positive is positive. 7 times 4 is 28. I times I is I squared. Okay, we got rid of the parentheses. We have to combine like terms. So right now, these are like terms. They're both positive. 21 plus 8 is 29i. But remember, whenever you see an I squared, replace it with a -1. So I squared becomes -1. So positive times negative is a negative. 28 times 1. So basically, all an I squared does is change the sign of the number in front of it. In front of it. So that's all an I squared does. So I squared, get rid of the I squared, and just change that sign. That's all it really does. Combine like terms. Positive 6, negative 28. 28 is bigger, so the answer is negative. 28 minus 6 is 22. 29i. And here's our answer. We can also multiply by constant coefficient. Our coefficients could be imaginary numbers as well. So distribute this term into both numbers in there. Negative times negative is a positive. 3 times 3 is 9. I. Negative times positive is a negative. 3 times 4 is 12. I times I is I squared. The I squared is equal to -1. So it changes the sign in front of it. It just becomes positive 12 now. And there's your answer. Typically, we write the real number first. So they both mean the same thing. It's just that the bottom one looks more correct. Your answer will never have an I with an exponent. You'll never have I to this anything. It has to be, if you have an I, it has to be by itself. You can't have any exponents. So let's look what happens here then. Let's say we had this example. Again, order of operations always start inside. You have to do inside this parenthesis, so left to right. Here we have another parenthesis. We have to do that first. We can't do anything there since it's not like terms, so we have to get rid of it. We have to distribute. We have to get rid of the parenthesis. So positive times positive is positive. 4 times 5 is 20. I. Positive times negative is negative. 4 times 6 is 24. I times I is I squared. We can't combine any like terms, so ideally right now we change this to -1 and go further, but I was going to show you this. So let's just get rid of this one. Let's distribute this. So positive times positive is positive. 2 times 3 is 6. I. Positive times positive is positive. 2 times 20 is 40. I times I is I squared. Positive times negative is negative. 2 times 24 is 48. 1 I times 2 more i's is I to the third. These two have to be rewritten. So we have 6i. The I squared becomes -1, so it just changes that sign, so it's -40. What about I cubed? What is I cubed? Because if we look at it here, this one, what would have happened here? This one would have changed that sign, would have had a positive. So we would have had a positive 24 times 2, which would have been a positive 48i. So somehow this one became a positive I. Or it changed it from negative to a positive I. So then we'd combine our like terms. Here's -40, the real number. They're both positive. 48 plus 6 is 54. So there's your final answer. Let's look at this. We start off with I. Remember, what if I gave you that? Remember, your answer can only have an I, no exponent. So we have to rewrite this as something else. Let's look at this. So we begin with I. I squared was -1. That's what we found out earlier. Let's look at what I cubed is. I cubed is I times I squared. So we have I, but what is I squared? I squared is -1. So I cubed is -1. What is I to the fourth? I to the fourth is I times I cubed. I cubed was -I. So we have positive times negative is negative. I times I is I squared. But I squared is -1. So I to the fourth is equal to 1. Let's go on 4 more times and I'll show you a pattern. I to the fifth is I times I to the fourth. I to the fourth is +1. So I times 1 is I. I to the sixth is I times I to the fifth. I to the fifth was I. So we have I times I is I squared, which is -1. We're almost done with this part. I to the seventh is I times I to the sixth. I to the sixth, we figured out was -1. So I times -1 is -I. And I to the eighth is I times I to the seventh. So we have 7 i's in another one. I to the seventh, we figured out was -I. Positive times negative is negative. I times I is I squared. Negative. I squared is -1. Negative is +1. So let's look at the pattern here. Seventh, I, eighth. I is just I. Because remember, you cannot have an exponent greater than 1. That has greater, that's just 1. I squared was -1. I cubed was -I. And then I to the fourth was +1. I to the fifth was I. I to the sixth was -1. And I to the seventh is -I. So if you look at these, they repeat in groups of 4. Sure. Yeah. The way it goes is this. If you want to easy remember, say, like if you win a race, you always say, I won, I won. And the middle two are negative. So this one is exponent is 1. This exponent is 2. Exponent is 3. And exponent is 4. Yeah, every 4 they repeat themselves. So it'd be I won again. Middle two are negative. So how does this help us? So to find I to the 54th, here's your step. So to find I to the 54th, divide the exponent by 4. Why 4? Because they go in groups of 4. So 4 goes into 54 how many times? 4 goes into 5 once. 4 goes into 14 3 times. 4 times 3 is 12. This is the number we're looking at. This is the remainder. If your remainder is 1, 2, 3, or actually 0 since it's 0. If you divide by 4, you can't have 4 as a remainder. So if it's 1, your answer is I. If it's 2, it's -1. If the remainder is 3, it's -I. And if it's 4, it's +1. So for our example, I to the 54, the remainder is 2. So instead of an I, we have a -1. That's what it equals. How about 128? What would that equal? What would that be? Let's see. How many times does 4 go into 12? 3. 4 goes into 8 twice. The remainder is 0. The remainder is 0. Answer is 1. That's if you have higher. So that's multiplication, addition, subtraction. Now the rules change. We're doing division now. Division of our complex numbers. We have 4 possibilities here. Actually, 3, if we just look at the last one. These are the 3 possibilities we can have. I combine these two because we can have C plus D or C minus D. It's still going to be the same rule. In other words, if you divide a complex number by a real number, remember, the real number and imaginary. So if you divide, say, 4 plus 8i divided by 2. Then just divide both parts separately if can. What if you had this kind of question? So we have 2 plus 9/2. As you could leave it in either one of these 2 ways. Typically, if it's not going to be evenly distributed, cancel like this, just leave it like that. It makes it much easier to look at. Actually, we have a couple more. So what if we had a constant on top? A monomial imaginary denominator. We just have a single term. Monomial means one term. The rule is this. You cannot have an I on the bottom. If you have an I on the bottom, it's a monomial. If you have a monomial on the bottom, then multiply both the top and bottom by I. Let's make the bottom 13. So we're here, we would have canceled the threes. Then we'd have 1 over I. That would have given a little problem. We'll do that a little later. So we have an I on the bottom. So we multiply the top and bottom by I. We're multiplying by I over I cancel. This is multiplying by 1. So it's not changing anything. You're just changing the way it looks. So on the top, we have 3I. On the bottom, we have 13I squared. Remember, since this is squared, the coefficient changes signs. It was a negative 13. And you don't want negatives on the bottom. So your answer is that, negative 3I over 13. What if we had 1 over I? Then multiply I over I. We get I over I squared, which is I over negative 1, which is negative I. Pretty straightforward. What if we had I on top and bottom? I knew you were going to say that. Can we cancel out the I's? I know. Because your mind was thinking, okay, I gotta multiply that, I get that. No, if you just have I's, single monomials, top and bottom, cancel out the I's. And then we can simplify. This equals 1/2. Okay, let's say we have a complex number on top with a monomial imaginary number on the bottom. Now you do what? Nope, can't, because this is an equation up on top. Well, we can't do anything inside there. There's only 1 I, so there's no like terms. So we can't do anything on top. They're not like terms. We can't cancel out the i's because this is an equation up here. We get rid of the I on the bottom. So this I distributes to both of those on top. 3 times I is 3i. 4 times 4i times I is 4i squared. 5i times I is I squared. But I squared changes the sign of the number in front of it. So it's a minus 4. This one becomes a minus 5. Because I squared becomes negative 1. All right, now this negative sign goes up on top. And it changes negative 3i. Negative times negative is a positive 4. Because you typically want to have the real number in front and the imaginary number in back. So even though this is not a wrong answer, it just doesn't look right. You mean this one or this final answer?
So many divide, you just make the equation on top.
Into a complex number, right? All right, yeah. So again, that's only if you have a monomial imaginary on the bottom. Then you just multiply top and bottom by I. What if we have a complex number binomial on the bottom? I use top and bottom because I don't want to write out numerator, denominator. I always use top and bottom because it's easier to write. All right. Now, whenever you have a binomial, imaginary complex number on the bottom, 2 terms. Remember, since they're equations, they have to stay together. How do we get rid of the I on the bottom? Here, we have to multiply by the conjugate of the bottom term. Conjugate is simply change the sign of the I term. So if we had 2 plus 5i, we would multiply by 2 minus 5i. Just change whatever the sign is in front of the I term, change it to the opposite sign. Let's see what's going to happen here. 2 times 2 is 4. Positive times negative is negative. 2 times 5 is 10. I. So that's it for the first one. Positive times positive is positive. 5 times 2 is 10. I. Positive times negative is negative. 5 times 5 is 25. I times I is I squared. Negative 10 and positive 10 cancel each other out. I squared changes this sign to a plus. So we have 4 plus 25 is 29. So basically, it's always going to do that. It's if you have a plus bi times a minus bi, it's always going to be a squared plus b squared. Because the I times I, middle term will always cancel. So here, since we have a denominator that's a complex number, we have to multiply top and bottom by the conjugate. So multiply top by bottom by bottom. So 3 times 2 is 6. Positive times negative is negative. 3 times 5 is 15. I. Positive times positive is positive. 4 times 2 is 8. I. Positive times negative is negative. 4 times 5 is 20. I times I is I squared. Now, if we remember the rule down here about imaginary numbers, the conjugates, we can just go ahead and write this shortcut. Or we can work it out. Which one do you want to do? Okay, so A is 2, B is 5. So it's 2 squared plus 5 squared. So we have 6. Combine the like terms. We have those two. 15 is bigger, so it's negative. 15 minus 8 is 7. I. The I squared changes the sign of its coefficient. So on the bottom we have 4 plus 25. Combine like terms. 6 plus 20 is 26. Minus 7i over 29. And there's our answer. It looks tough, but once with practice, it goes much faster. Here's another example. Oop, yeah. What I like to do is whenever I have complex numbers, I always put them in parentheses. So I don't mess up anything. Go ahead and solve it. Bless you. So we have complex numbers top and bottom. So we multiply by the conjugate of the bottom, which is -4 plus 2i. Just change the sign in front of the I. Now we can go ahead and multiply these out. Positive times negative is negative. 2 times 4 is 8. Now that second number. Positive is positive. 2 times 2 is 4i. That does it for him. Negative times negative is positive. 3 times 4 is 12. I. Negative times positive is negative. 3 times 2 is 6. I times I is I squared. And on the bottom, since they're conjugates, we take the first number, square it, and the second number, square it. So this changes that sign to a plus. So we have -8, add combine like terms. They're both positive. 4 plus 12 is 16i plus 6. It changes sign. And on the bottom, -4 squared is 16. 2 squared is 4. 16 plus 4 is 20. Combine like terms. 8 and 16. 8's bigger, so the answer is negative. 8 minus 6 is 2. Yes, that looks good. But if you notice, all of these numbers are even numbers. So on the top, what do they have in common? They both have a 2 in common. Because they're both even, so they're both divisible by 2. So if I took both of those numbers and divided each one of them by 2, because I took out the 2, I would have -1 plus 8i, because 16 is 16. I can check that. 2 times -1 is -2. 2 times 8 is 16. So whenever you factor anything out, whatever goes inside is just divide everything there by what you factored out. Whatever's left goes in there. And on the bottom, we have 2 times 10. So our answer is -1 plus 8i over 10. That is our simplified answer. Yes. Whenever you have fractions, always simplify. Or 3 or 4. Yeah, if they have a common divisor, then yes. Whereas if we had that as a final answer. Everybody's divisible by 5. 5 goes in here, 5 times 3. 5 times 5. 2 times 5. They all have a 5 in common. So basically, I could just get rid of 1 5 from everybody. Which leaves me with a -3 plus 5i over 2. Okay, so that's section 1. Section 2. Chapter 3, Section 2. Quadratic equations functions and zeros. The reason we talked about complex numbers before this one is because to solve quadratic equations, a lot of times we use square roots. And so if we have a negative square root, we know it's imaginary. Quadratic equations have this form. The function equals ax squared plus bx plus c. That's the standard form. We can also write it as a x minus h squared plus k. They both mean the same thing. What is the graph of a quadratic equation? It's a parabola. In this course, I want you all to get to a point where you could look at the equation and tell me, just looking at it, what kind of graph it's going to be, how many solutions can we have, what's the shape of the graph. In any polynomial simply means a large equation. For example, that's a polynomial. I'm jumping ahead, yes, because this is what we're going to talk about next chapter. But what I want you to do for this part is look at the first. So notice how the exponents are decreasing. 5, 4, 3, 2. This is an invisible 1, and there's none here, 0. So this is what's called a leading term, and this is the constant. Those two are going to give us all the information we need without doing any math. The leading term in that example is 2x to the 5th. That number in front is called the leading coefficient. Your variable. The exponent is called the degree. Degree of the polynomial. The degree tells us the type of polynomial the shape of the graph the maximum number of solutions or x-intercepts possible and the maximum number of vertices possible. So like, all of this stuff is given to us by the largest exponent. The degree is the largest exponent. Ooh, that's horrible. Exponent. The coefficient, the leading coefficient, tells us the direction of the graph. Oh, also another thing, the degree tells us, the degree also tells us what's called the end behavior of the graph. And the constant tells us the y-intercept. That's all it tells us. So for our example, if our degree was 5, it tells us we're going to have at most 5 x-intercepts, which are solutions. At most 4 vertices. And then that both ends of the graph point in opposite directions. Instead of showing that right now, I'm going to change this from now to a 3 because remember, if it's odd, basically I'm saying if it's odd. These are all true if it's odd. So instead of this, I'm just going to use the letter n. So if we have a degree n, then we have at most n intercepts. We can have at most n minus 1 vertices. And if it's odd, they point in opposite directions. So let's look at that function. we can have at most 3 x-intercepts. The graph can look like this, which is 1, 2, 3 x-intercepts. Three solutions. This is n minus 1. We can have then 2 vertices. And the ends point opposite directions. Or our graph can look like this. Here's one solution, and there's one solution. So we can have 2 solutions and still have 2 vertices. But because it's odd, we have opposite directions. Or our graph can look like this, where we only have one solution. And in this case, we still have 2 vertices. But because the degree is still odd, it points opposite directions. If the leading coefficient is positive, it looks like this. The graph is increasing. What that means is as x goes to infinity, the graph is pointing up. If the leading coefficient is negative, in other words, if we had something like this, if it's negative, the graph is decreasing. Which means our graphs could look like this. So the coefficient, leading term, if it's positive, it's an increasing function. If it's negative, it's a decreasing function. And the degree tells us the shape of the curve and how many answers we can have. So that's if our degree is odd. If our degree is even, let's say a equals x to the 4th. Then we can have at most 4 solutions. Remember, solutions and x-intercepts are the same thing. At most 3 vertices. We can have at most 4 solutions, 3 vertices. And that's all it's going to tell us there. The reason we say this is because with even functions, With even degrees, both ends of the graph point the same direction. That's end behavior. Both ends point the same direction. Unlike odd degrees, they point opposite directions. So we can have 4 solutions, which means we have 3 vertices. We can have 3 solutions. We can have 2 solutions, or we can have no solutions. I'm sorry, we have 2 solutions, or we have 1 solution, or we can have no solutions. So even degrees can have at most n, but it can have 0 because both ends point the same direction. Odd degrees have to have at least 1 solution because they point opposite directions. It's going to cross the x-axis eventually. So back to what we're talking about, quadratic equations. Quadratic equations, QEs. So with what I just told you, what can you tell me about these 2 graphs? The shape of them, directions. Nope. What degree are these? The degree is the highest exponent. Yes, it's 2. It's even is 2. Since it's even, it says both ends point the same direction. Are they going to open up or is it going to point up or point down? In the first one, since it's negative, yeah, this one's going to point down. We can have at most 2 solutions or 1 solution or no solutions. This one, on the other hand, is positive, so it looks something like this. But the only thing we know for sure is this y-intercept is -7, and this y-intercept is +4, whatever our graphs are. So to graph quadratic equations, you need the x-intercepts, or the solutions, the vertex, that's the high low point of the graph, and you need some points. The beautiful thing about the quadratic equations is it's symmetric about the y-axis. So if I had a point here at 5, 2, I know by symmetry that there's also a point here at -5, 2. If I have one at 7, 6, I know I have to have one here at -7, 6. They have to be symmetrical. The vertex is right here. The axis of symmetry is the vertical line through the vertex. So the vertical line through the vertex is called the axis of symmetry. From that point, in either directions, you have to have the same points. Let's begin with something easy. Y equals x squared plus 5x plus 6. To solve, in other words, to find the x-intercepts, we factor the equation. All right, factoring sometimes works. And let's first look at some examples here about factoring. We'll come back to that example in a second. Multiply these 2 points together, or these 2 binomials. I want to do this so I can show you, so we can look for patterns here. And also give you practice of multiplying or foiling these binomials. So the first one, x times x gives us x squared. X times 3 is 3x. Now the second number, 2 times x is 2x. 2 times 3 is 6. Combine like terms. They're both positive. So 3 plus 2 is 5x. And the last number is 6. Do the next one. X times x is x squared. X positive times negative is negative. X times 3 is 3x. Positive and positive is positive. 2 times x is 2x. Positive times negative is negative. 2 times 3 is 6. Combine like terms. 3 is bigger, so it's minus. 3 minus 2 is 1. X times X is X squared. Positive times positive is positive. 3 times X is 3X. Negative times positive is negative. 2 times X is 2X. Negative times positive is negative. 2 times 3 is 6. 3 is bigger. 3 minus 2 is 1. And the last one. X times X is X squared. X times negative 3, or positive times negative is negative. 3 times X is 3X. Negative times positive is negative. 2 times X is 2X. Negative times negative is positive. 2 times 3 is 6. Negative 2, they're both negative. Add them together. There. The reason we do this is so you can first get practice multiplying these things, but more so we start seeing patterns. When factoring quadratic equations with a equals 1. Remember, a is the coefficient, leading coefficient. So all of these examples have a equals 1. First up. So, okay, what is factoring? Factoring goes from this equation to that equation. That's factoring. So the first thing we do is look at the second sign. So I'm gonna pick one of these. I'll use the x squared minus x minus 6. Look at the second sign. If it's positive, then the signs are both the same, and they are the first sign. So if the second sign is a positive, that means both of the signs inside these parentheses are the same. But since it's not, if it's negative, the signs are opposite. And the larger answer gets the first sign. So since the second one's minus, we know the signs are different. One's positive, one's negative. Second step. What times what equals x squared? Those go in the first spots. So what times what is x squared? X times x. Now, third step. What two numbers multiplied give you the constant term and when you second sign, you get the coefficient of the middle term. It sounds cryptic, but it makes sense once we look at it. So what times what equals 6? That when we subtract them, we get 1. 2 times 3. And since we have two different numbers, since the second sign is negative, the bigger number gets the first sign. So the answer is 2 times 3. Since the first sign is negative, the 3 goes there. That's how it works. This one says, since the second sign is positive, both signs are the same. They're the first sign. What times what equals x? That's x times x is x squared. What times what equals 6? When you add them, you get 5. 2 and 3. We just did this one. X plus 2, x minus 3. Second sign's a minus, so the signs are opposite. What times what is x squared? X times x. What two numbers multiply to give you 6? When you subtract them, you get 1. 3 and 2. First sign is positive, so 3 gets that one. The bigger number gets the first sign. Second signs are positive, so they're both the same. They're both minuses in this case, since that's the first sign. What equals x squared? X times x. Two numbers multiply to give you 6. When you add them, you get 5. 2 and 3. So that's how factoring works. Let's give you some more numbers. Factor that one for me. So what about the signs? Very good. What goes in the first spot? So now comes the hard part. What times what equals 12 when you subtract them, it equals 4. 6 times 2, 6 minus 2. Since the signs are opposite, the bigger number gets that sign. So the 6 goes here, the 2 goes there. Okay, so that's how we factor. Once we get to this point, our x-intercepts are found by setting the factored terms equal to 0 and solve. So x plus 2 equals 0, x minus 6 equals 0. Solve, subtract 2 from both sides, x equals -2, and x equals 6. Again, which we should have known because of transformations. It's always, if you have inside the parentheses, it's always the opposite number. It's always the opposite. You okay with that then?
Yeah.
Okay. What if we have, if a does not equal 1? What do we do there? Here's the easier way that I show my students. First, place the a value in both parentheses. So we put 6 here and 6 here. So it's 6x, 6x. Do the signs. Since the second signs are positive, they're both the same. They're both positive. Now, here's the tricky part. Remember, our equation looks like this. Multiply a times c. The first times the last number. Once you do that, you have to figure out what two numbers multiply to equal, let's call this x. When you add them, you get your b term. So we have that, we have the 6 times 6, the pluses are same signs. So we take 6 times 2 is 12. We have to figure out what two numbers multiplied gives you 12. When you add them, you get 7. Three times 4, 3, 4, right? Since they're both the same signs, it doesn't matter. Those values are going to start there. Now, factor both parentheses. So what do the first one? Do they have anything common? 6 and 3? They both have a 3 in common. So we take out the 3. Remember, whenever you factor anything out, it's like dividing. 6 divided by 3 is 2. 3 divided by 3 is 1. How about the second one? 2. Very good. So I divide by 2. I get 3 plus 2. 3x plus 2. Remove the factored numbers. So just get rid of them. And there's your factor. That's it. All right, let me put another one up there. So we have, this is example. 6x squared plus 7x minus 20. Well, yeah, we have to first put everything together. So we have 6x, 6x. What about the signs? Right, now we do that. 6 times 20 is 120. So give me two numbers times equal 120. Now, since this is a minus, we subtract them, we get 7. So what we gotta do is figure out, let's look at all the numbers. We have 1 times 120, 2 times 60, all of these equal 120. 3 times 40, 4 times 30, 5 times 14. No, 5 was in 24. 6 times 20, 8. 8 times 15. This one. So 8 times 15. 15 minus 8. Since the first sign's plus, the 15 goes there and the 8 goes there. Then what? Right. So we get 2x plus 5. Three x minus 4. And get rid of those. So our factors are, yeah, again, this is the hardest part here. Yeah, that's the hardest part. Once you get that, then you're right. Once you saw 8 and 15, you knew the difference was 7, you're done. There's another method of factoring, because we can't factor this one. Because what two numbers multiply to 5 when you subtract make give you 3? Nothing exists. So we have to use another method. Or let's use 8. I want to use 8. This is called complete the square. First step. If A does not equal 1, divide each term by A. Since A equals 1, we're good to go. If not, then we'd say each term divided. Set the equation equal to 0. Move the constant to other side. So we're going to add 5 to both sides. Add b over 2 squared to both sides. So what's our b? So we add 8 over 2 squared to both sides. The left side only do inside the parentheses. Don't square it. Right side, work it out. So this would be 4 squared would be 16. 8 plus 16 is 21. So far, so good. On the left side, this is where you complete the square. the first term first sign and last term squared. What I mean here is the whatever's under the square goes inside the parentheses. So we have x plus 4 squared. Follow that so far? Because once we get to this part, we just take whatever's under the squares and put them inside the parentheses. Because at this stage, if we move the number back to the other side, remember this stage right here, because I'll show you that the next formula. Now, solve for x. The way we would solve for x in this case, we have to get rid of this. We have to get the x, since it's inside, we have to get rid of the square. We square root both sides. Now, since you square rooted something that's squared, you have to put a plus or minus in front of the other side, because it can be positive or negative. X plus 4 equals plus or minus square root of 21. Move the 4 over. So x equals -4 plus or minus square root of 21. Those are your two x-intercepts. You have x equals -4 plus square root of 21. X equals -4, or -4 minus square root of 21. Those are your two x-intercepts. That's complete the square. Now, what we set up here, if at this stage, remember, it equals 0. If we move this 21 over, this is the second form of our quadratic equations. Because our first form was ax squared plus bx plus c. Another form that we can use is x minus h squared plus k.
Oh,
And that's exactly what that is. So the hk here is your vertex. So in our example, we had x plus 4 squared minus 21. Our vertex is at -4, -21. All right, so that's that form. You had standard form, now you have the other form. So are you okay with the complete the square?
yeah,
You want to do another one?
yeah.
Well, let's do another one with a coefficient in front of it. So y equals 2x squared minus 12x plus 6. I'm sorry, that's what we should put there. So remember, first step, since a is not equal to 1, divide everybody. So divide by 2, divide by 2, divide by 2. We have x squared minus 6x plus 3. Set equal to 0. So we have x squared minus 6x plus 3 equals 0. Okay, I'll make this perfect. When we divided it, what's really happening is we just really factored out that 2. So there's always a 2 out in front. Move the constant term. Move C. So we have x squared minus 6x equals -3. We move the constant term over. Add b over 2 squared to both sides. Left side, right side. So here we have x squared minus 6x plus 3 squared. So this is 3 squared, makes it 9. So it's -3 plus 9 makes it 6. Complete the square. So it's whatever's under the squares and the first sign. Solve. Square root both sides. Remember, you have to put a plus or minus in front of the answer. And then add 3. So x equals 3 plus or minus radical 6. These are your x-intercepts. That's it. But now you're going to ask me in a minute, why do we have to know this when I'm going to show you a shortcut? We need to know this because at this stage here, remember when we had x minus 3 squared equals 6? If we move the 6 over again, now you can tell me where the vertex is. It's at 3, -6. The HK. So we do this so we can find the vertex, and it'll help us further on, and it makes it easier to find x. So we learn how to find the vertex. I'm going to do something real quick. Finding the vertex with that. Oh, you know. To find the vertex here, the formula for the vertex is this. Remember, vertex is a point, so you have to have an x and y component. So your x value is negative b over 2a. Once you find that, plug that back into your equation, and that'll give you the y value. That's what this says. Remember, f of x is the same thing as y. So let's look at our vertex. The x value is negative b over 2a. Negative, what is b? What's a? We have negative 8 over 12. They both have a 4 in common. So that's our x value. I should have put more thought into this one because it's going to give us a fraction. So negative 2/3 squared makes it positive 4 over 9. Positive 8 times negative 2 is negative 16 over 3 minus 5. Simplify this one. So they both have a 3 in common. We have 2 times 4 is 8 over 3 minus 16 over 3 minus, okay, this is 5, so we have to have a common denominator of 3. So it's 15 over 3 minus 15 over 3. Bless you. 8. Oh, sorry. 8 minus 16 is negative 8. Negative 8 minus 15 is negative 23. So our vertex is at negative 2/3, negative 23 over 3. So we know where our vertex is. This value here is called the axis of symmetry. The x value of the vertex. And in this case, it's that. Why is it called the axis of symmetry? Because what if our vertex was at negative 2, 1? And it's a quadratic equation. So it would look like our graph would look like this. That's the vertex's lowest point. So this half has to equal this half. So I can rotate it about this and have the same picture. So that's why it's called the axis of symmetry. So far, so good. So we found the vertex, we found the equations. Now let's do the shortcut. The quadratic formula. Factoring works great if it's factorable. If we can get perfect numbers. If not, we can try to complete the square. But we just saw if we complete the square, if you get a fraction, you have a lot more work. The quadratic formula comes from the complete the square. You're looking for the x-intercepts. Negative b plus or minus the square root of b squared minus 4ac. So when you're given an equation, label A, B, and C, just plug them in there. Let's do that one again. Find me the x-intercepts. Or in the question, I said, solve this equation. So the first thing you would do, here, I'll put the steps. Label A, B, C. So A is equal to 6, B is 8, and C is negative 5. Plug into the quadratic formula. Always write it down first. All right, here I wrote it down up here. So I have negative 8 plus or minus 8 squared minus 4 times 6 times negative 5 all over 2 times 6. So negative 8 plus or minus 8 squared is 64. Negative times negative is a positive. 4 times 5 is 20 times 6 is 120 over 12. Negative 8 plus or minus square root of 184 over 12. At this stage, let's see what 184 breaks down into. Since it's an even number, we know 2 goes in there. 2 goes into 18 9 times. 2 goes into 4 twice. So there's 1. 2 goes into 92, since it's an even number. 2 goes into 9 4 times with 1 left over. 2 goes into 12 6 times. 2 goes into 46 23 times. Can't go any further. Two times 2 times 2 times 23. This is a square root. If we see 2 of a kind, we can take it out in front. So there's 2 2s and we take it out. And we're left with 46 inside there. Eight and 2 both have a 2 in common. So we factor out the 2. Two cancels with the 12 6 times. So our x-intercepts are at those two values. So that's all there is in the quadratic formula. So it's always works. The quadratic formula always works. The complete the square works, but you may have to have fractions everywhere. Factoring only works if it's factorable. Right? This thing does a little bit more. In the quadratic formula, the number here is called the discriminant. It tells us the number of real solutions. If b squared minus 4ac, if that number is positive, we have two real solutions. If 4ac equals 0, we only have one real solution. And if the discriminant is negative, we have 0 real solutions. That means we're going to have two imaginary solutions. Now, it sounds pretty impressive, but if you think about it, this number here is inside the square root, right? So if we had, let's say, number 4 there, that's a positive number. So we can take a square root of it. We're going to have two solutions because we have a negative b plus 2a, or 2, and a negative b minus 2. So that'll give us two answers. If it's equal to 0, then we only have 2a, that. And this is our axis of symmetry. Remember the formula we had for the quadratic equation, the vertex, negative b over 2a. Because this one, since it's 0, this one lands on the x-axis. The vertex is a point on the x-axis. We only have one solution. And if it's negative, obviously then we have imaginary numbers. So we'll have two imaginary answers. So yeah, so I mean it's pretty cool when you first see it, but then because if it's inside the square root, if it's a positive number, we have two answers. If it's a zero, we only have one answer. If it's negative, then it's imaginary. Well, yeah, you can once you take out the I. Okay, and actually we actually did 2 and 3 there because section 3 deals with both of these forms. We know how to find the vertex here. Find the x value and then plug it back into the original equation. We know this one because the vertex is hk. If a is positive, it opens up. If a is negative, it opens down for both of these. The y-intercept is this one. Is C in this first one, but in the second one, you have to work it out. Because the way you find the x-intercept is set x equal to 0. So that means this is gone, and just left that. But with this one, the y-intercept can actually be worked out. -3 squared is 9. 18 plus 4 is 22. So the y-intercept is at 22. So you could choose either one. And now we know how to go from here to here by using the complete the square. So that's how we graph them. We find the vertex, find the x-intercepts, draw the graph, and find some more points. And that's the graphing. Okay, we'll do some examples there, but that finishes the first 3 sections. So to graph, a quadratic equation, find the vertex, find the x-intercepts, the solutions, find the y-intercept, plot those points, find 1 or 2 more points, and then graph. That's all there is to it. Remember, the vertex is 1 point. The x-intercepts can be 1, 2, or no points. The y-intercept is 1 point. Again, let's say here. We can't use that one. Let's say our vertex is at -3 and our y-intercept is at 4. We know that's a point on a graph, isn't it? There has to be, once it's the -3 is the axis of symmetry, there has to be a point here. Also at 4. Since it's -3 here, we go -3 here, that's at -6. So this point is -6, 4. This one is 0, 4. So again, by symmetry, we could tell plot the points. And once you have the vertex, the intercept, its mirror point, you really need just one more point. Actually, this is all you really need. One more point could do it. Plot those points and you're done. So that's section 3. Analyzing graphs of quadratic equations.
It's a lot. I'm excited. It's just like a lot of process.
Well, no, it is. And once you start looking at it, this reason I wanted to go through those first 3 sections because they're all tied in together.
Mhm.
And again, we'll answer questions next time also if you want. But then next time we'll also, if we have time, then we'll finish up the chapter. Only 2 more sections left. And then that'll put us in very good position to finish up the semester maybe a week early. Okay, everybody. That's it for today. Have a great weekend. Be safe. Enjoy the beautiful weather. And I will see you guys next week.